Okay, so also good morning from my side. I have to get used to the cold climate, yeah. Because when I go back to Germany, it will be pretty cold probably. And I have to store also some heat. Some people asked me already whether I couldn't bring some sun with me. I don't know the current temperatures in Germany. It's probably around 5 degrees or between 5 and 10. So nice and cold. Okay, so today I wanted, in the first part, to speak about phase transitions or phase transformations. For me, it's more or less synonymous. Some people distinguish, and we use both terms a bit in a different sense. But to be honest, I don't know precisely. I mean, I show a kind of, I call it a pedigree. We have so many phase transformations in solids which control the properties of a solid to a very high degree. So it's really worth to know something about phase transitions, phase transformations. In the beginning, I think in one of the first lectures, I showed one phase transformation which is familiar to all of you, from solid to liquid to gas. That's typically what people understand if we speak about phase transitions or phase transformations. And I wanted to show some general ideas about phase transitions, phase transformations. And also, that's why I show this complicated graph here. It's nice to show also the possibilities we have with MD and with MC. I'm not sure whether this graph is complete. I just put it here without thinking too much. So if we speak about phase transformations in solids, so not the melting and so on, there are what we call structural phase transformations, which change the atomic arrangement in a sense. And then there are also electronic phase transformations. Perhaps you are familiar with magnetic. Above a certain temperature, magnetic material loses its magnetism at the Curie temperature, or in a superconductor above a certain temperature or above a certain magnetic field, it loses its superconductivity. So this is something I want to leave out. I want to concentrate here on the structural phase transformations. And there is one general distinction which is not very strict. I think there are combinations of both as well. But here, for this nice hierarchy of transformations, makes sense to distinguish between diffusive phase transformation and displacive phase transformations. I think again the language is not very homogeneous, but anyhow. So by diffusive phase transformations, I mean transformations where the atoms are moved by distances of at least of the order of atomic distances. So here among these diffusive phase transformations, we still can distinguish, I call it homogeneous and heterogeneous. I'm not sure whether these are the right terms. What I mean here is transformations, diffusive phase transformations, but where the overall concentration in a small part of my system does not change or does change. So this one is homogeneous or heterogeneous. Here basically, I don't know whether there are other examples. I mean ordering transformations. I'll show examples later on. And these are precipitation reactions, so where one part enriches in B atoms and the other part depletes in these B atoms. So think of aluminum copper, for example. The example I always took. So in aluminum copper, above a few percent of copper, the copper forms precipitates, which are then very important for the mechanical properties of these 2000 series of aluminum alloys. That's this part here. And these ordering transitions, they are, I'm not sure, I think they are a bit less common or a bit less studied. They are, for example, they take place, for example, in alloys like aluminum, nickel aluminum, copper gold. Copper gold is a classical example. Copper gold at 25%. forms the so-called L12 structure. So it's on the FCC lattice. And in this L12 structure, you put most of the composition of copper 3 gold. You put most of the gold atoms on the corner sides of the FCC lattice, and the copper atom on the face-centered sides. And above 430 or so, this, what we call a superstructure, disappears, and the atoms are just homogeneous or randomly distributed over all types of sites. Or another example is copper zinc, brass, beta brass at 50%. In the ordered structure, the zinc atoms occupy the corner sites, and the copper atoms occupy the body-centered sites. And above, I think it's again around 400 something, this superstructure disappears, and the copper and the zinc atoms are equally distributed. This can be measured, for example, by electrical resistivity. You see a clear change in electrical resistivity, and other properties also change. So these are the ordering transitions and the precipitation reactions. I call it here reaction. It's not, normally we don't speak of transitions or transformations here, but it is a phase transformation. So these are diffusive. And on the other side, the displacive phase transformations, where the atoms are slightly shifted from their equilibrium positions. There, again, I come to this and explain it a bit more in detail, what is called shuffle transformations and distortive transformations. One of these, probably you know, is a martensitic transformation. Again, in an example, I will show how it proceeds. This distinction basically means, do more or less all atoms homogeneously move away from their starting positions? Or is there a kind of oscillation, spatial oscillation? Yeah? So one move to the left, some move to the right. That's what we call shuffle transformations. And for both, we also have examples. And then these distortive transformations can be also further distinguished into dilatational and deviatoric transformations. Dilatation means that the volume is not conserved. This is, for example, the case in the zirconium oxide and probably in other oxidic systems. The volume of the unit cells changes. This is exploited in these yttria-stabilized zirconia, which have a very high fracture resistance, or for ceramic materials, high fracture resistance, because you can induce this transformation by external strain. So in front of a fracture, of a crack tip, this transformation takes place, and the volume is expanded, and this closes this crack. So that's a nice trick here, where you exploit these dilatational transformations. And these deviatoric transformations, again, not 100%, but mostly the volume is not changing. And as a standard example, these are the martensitic transformations. So this is, I don't know whether I missed some, at least big part of the possible structural transformations. To come back to our lecture here, these displacive transformations, they can be nicely studied using molecular dynamics, because they take place usually pretty fast, and they don't require very large systems. It just has this slight displacements here. Very often they proceed with the velocity of sound in the system, so several thousand meters per second. That's why the time scale required to, for a system of, I don't know, 10 nanometer size or 50 nanometer size, the time is sufficient, which we can cover in MD. The diffusive phase transformations on the other side typically are very slow, because diffusion in a solid, as we saw last week, is pretty slow. So studying these phase transformations by MD is hardly possible. So that's where MC comes into the play. And of course, there are combinations in hybrid algorithms where we try to cover, if you have a displacive component and a diffusive component, where we try to cover the displacive part using MD and the diffusive part using MC. But that's a bit artificial, I would say. So more or less, we can say the left-hand side is Monte Carlo, the right-hand side is a domain of molecular dynamics. And I will start to speak about Monte Carlo simulation later on this morning. But before that, I wanted to make further general remarks on phase transformations, which might be helpful. And I hope it was a bit fast. I just prepared this the last days, this lecture. But I think it's a knowledge we should share here if you are not aware of that. So the first thing I already introduced in one of the other lectures, if we consider free energy as a function of temperature, dg dt or df dt is minus the entropy, so it's a falling function with temperature. So that's what it typically looks like with a slight curvature, but the temperature dependence of the, it's basically the internal energy is not very large. So we can also approximate it as a solid, as a straight line. So this is one phase. If we have another competing phase, for example, a liquid, the liquid has a higher entropy, so a steeper slope here, and at some point there should be an intersection. And that's what we call the phase transition temperature, because in equilibrium, the free enthalpy is minimized. So to the left of this intersection point, we have the red branch here, the solid phase. To the right, we have the liquid phase. So this is the lower branch here. And in between, we have the melting point if these are liquid and solid phases. So that's a very simple and general approach. I'm not sure. Here I show oh, sorry. Here I show a real sketch of these graphs here for the case of copper. And you see that the difference in slope between the liquid and the solid phase is pretty small, hardly visible. So here we have the solid phase. Here we have the liquid phase. And they intersect here at the melting point. It's in Kelvin here, 1300 something. It's much better visible for the gas phase because the difference in entropy between the gas phase and both the liquid and the solid phase is much more pronounced as a difference between liquid and solid phase. I found it interesting. Intuitively, one would assume that the entropy of the liquid phase is far higher than that of the solid phase, but it seems to be not the case. So we can say a bit more about, I repeat this little sketch here. So that's the solid phase and the liquid phase. And the equilibrium follows always the lower branch here. Here's the melting temperature. What else can we deduce from such a simple consideration? If we look closer to this melting point here, we have the solid phase and the liquid phase, and our equilibrium curve looks like this. You see here's an abrupt change in slope. And since dg dt is minus the entropy, we obtain a delta S, which is a slope on the left side. At Tc or Tm, yeah, I put it minus here to denote here the left side. Minus the entropy of the liquid at the transition temperature. So I put it as plus. So we have a abrupt change, a jump in entropy. And what does it mean? This, I guess, is known to everybody. This corresponds to a change in content of heat. And this delta Q is what we call the latent heat, in this case of the melting transition. So that's the first thing you should understand, that there is in this type of transition that there's a jump in discontinuity in entropy. We call this type, and come to the other ones in a moment. This type of transitions we call first order phase transitions. Discontinuity and this corresponds to latent heat. And to explain this term, first order phase transition, it's just inverting this sentence. If you find a discontinuity in entropy, we call it a first order phase transition. Yeah, it's just a definition of a first order phase transition. But if I say first, there must be also a second. So how can we achieve a second order phase transformation? Phase transition, phase transformation, I should at least here use. And as I said, the definition is just there is a discontinuity. Here is no discontinuity. What does it mean? If we make our sketch again. We have our red curve, and now we have another phase. I should not call it solid and liquid, because solid and liquid is always a first order phase transition, except at the critical point. No, not solid liquid, liquid gas. There it becomes a second order phase transformation. So how can we avoid this discontinuity? Just means we have a second phase here, and it's smoothly, hard to sketch smoothly merges here. If the tangent of the green curve and of the red curve is the same here, then we have no discontinuity in S. Okay? Yes, but in higher derivatives. In these higher derivatives, where it is visible, typically the second derivative, which is proportional to the specific heat. So if you measure the specific heat about such a second order phase transition, you see discontinuity, some strange behavior in any case. Perhaps I should give examples for both here. I mean, this one is obvious, liquid-solid phase transformation, but most of the phase transformations I showed here are first-order phase transformations. We can have a look, I don't know whether... Yeah, this is an interesting case. I will show it. Here we have both first and second order phase transitions. Here these precipitation reactions are, to all what I know, all first order. I think these are also first order transitions. I guess this one as well. But here in the electronic transitions, these are typically second order phase transformations. And big part of this theory was developed for the Curie temperature transition, yeah? The loss of ferromagnetism at a particular temperature. For superconductors, I think it's also second order phase transformation. I might try to give conditions when can we have such a second order phase transformation. And I don't want to go too much in detail, but it's obvious to have such a smooth transition from one structure, if we speak about a structural transformation, to another structure. There must be a continuous path. Yeah? I mean, if you change the structure from FCC to B, not sure. No, from FCC to BCC, there's nothing in between. Yeah? You cannot go smoothly from FCC to BCC. So this must be a first order phase transition. Yeah? For these ordering transformations, as I said, they are obtained by putting the majority on one sublattice and the minority on the other sublattice. And there you can smoothly approach zero. That's why we can have second order phase transformations there. So there must be a structural relationship or between the high temperature and the low temperature phase to have a second order phase transformation. One can formulate this in terms of symmetries. One must be the symmetries of one phase must be a subgroup of the other, of the symmetries of the other phase. Then it's possible. If they have different symmetries, for example, one has a mirror symmetry, one has no mirror symmetry, there's nothing in between. There's no half mirror symmetry. Yeah? So that's one of the conditions. There is a couple of criteria for second order phase transformations. Yeah, perhaps I should at least briefly write. I just make this mark here, symmetry. And if we think of this transition liquid to solid, liquid to gas, one sees in principle it is possible to smoothly go from a liquid to a gas. Yeah? There's no symmetry difference between a liquid and a gas. It's both disordered. But typically it is a first order transition because the density abruptly changes, and this is again related to other thermodynamic quantities. You have this jump in density, which is typically of a factor of 1,000 or so. Yeah. But at the critical point where the pressure curve ends, there is a second order phase transformation, and this allows experimental tricks like supercritical cooling or so, yeah, or supercritical drying. So you can somehow circumvent this jump in specific volume or so. Yeah. It's important if you have sensitive material and you want to avoid that it collapses in this phase transformation. Yeah. You have to go to a temperature and or a pressure above this critical pressure. There's this difference between gas and liquid disappears, and then you can smoothly circumvent this discontinuity in whatever quantity. I think it's used for micromechanical systems where you have very fine structures and you prepare them in some solvents, and then you have to get rid of the solvent. Think of such a micromechanical, I don't know, such a lever or so. If you would do subcritical drying, this would just collapse because you have this compression there. That's why they use this trick to go around this critical point. Okay, so this is one thing. Then I wanted to briefly go into a very simple but instructive description of these type of phase transformations. This is a bit, in German we say hauruck, which means a bit vigorous or so. So we assume that the free energy depends on a quantity which describes the state of our system, and we or he calls this an order parameter. For this simple example of ordering phase transitions, where some species enrich on one sublattice, it's very simple what we define as the order parameter. For other transitions, it's far less obvious. For this gas-liquid transition, It's just the density which is used as an order parameter. For a superconductor, it's a density of Cooper pairs. For a magnetic system, it's a magnetization, and so on. So with some effort, you find such an order parameter which characterizes the degree of order. This very much depends on the precise system you're studying. I want to call this order parameter psi. And what Landau assumed is that we can expand the free energy in terms of this order parameter. By a constant, which later on we forget about. Then quadratic term. Since this was developed for magnetic systems, this order parameter is symmetric, so it does not matter whether it points up or down, so only even terms appear here. Plus further terms. And the only point where he introduces temperature is this parameter alpha. It's a very minimalistic description, but it already shows rich behavior. This alpha 0 is positive. Beta is positive. Then we can look how this graph behaves for different temperatures. I think I did it this morning here. It's on the left side. So for a temperature above this transition temperature, which we call the critical temperature, this Tc, this curve has just one minimum here. At precisely this critical temperature where this parameter alpha changes sign. Yeah? So above this critical temperature, alpha, which is alpha 0 times T minus Tc, is positive. Below, it's negative. So precisely at the critical temperature, this curve still has a unique minimum here at order parameter 0. And as soon as you go below this Tc in temperature, this converts into a maximum, so changes its curvature here. And two further minima show up here. These are just the properties of fourth order polynomials. Yeah? But what does it mean? If we say the free energy or free enthalpy is minimized, it means for temperature above or at the critical temperature, the equilibrium order parameter is at 0. So the system is completely disordered. As soon as we go below the critical temperature, there's a finite degree of order. And if you think of a magnetic system, there can be magnetization upwards or downwards. That's why we have these two minima. And this can be translated into an equilibrium order parameter. No, psi. is a function of temperature. We have our critical temperature here. I did not write it here. So Tc is a critical or the transition temperature. So above, equilibrium degree of order is 0. And below, it's slowly now if we start from high temperature, it's slowly going up. And we have this here, and here we have a value of 1, perfect order, but only at very low temperature. This nicely describes, for example, the behavior of magnets. Yeah? Perhaps you, I don't know whether you know anything about magnets. So that's a nice coincidence. You can call this Tc T Curie, the Curie temperature, above which the magnetization gets lost. And for, I mean, you all know perhaps about these hard magnets, cobalt samarium or iron neodymium boron. Cobalt samarium has a Curie temperature about 900 Celsius or so, or 900 Kelvin, I forgot. So this is fine. But these iron neodymium boron magnets, which are far cheaper than the cobalt samarium magnets, they have a Curie temperature only of 300 something. And you see here, if you approach the Curie temperature, the magnetization, in this case the saturation magnetization, already goes down. So as soon as you are close to the transition temperature, and close does not mean too close, yeah, 200 Celsius or so, you lose a lot of magnetization. And that's one of the problems about this iron neodymium boron magnets, which from their other properties are superior to other. So they are used in electromobility, for example, in electrical motors. And if the motor is highly loaded, temperature raises, and then you lose magnetization in these magnets. Yeah? Or in wind turbines or so, the generators, they have the same problem. And one of the related problems is you have to add some amount of dysprosium into these materials, and dysprosium is one of the expensive rare earth elements. Neodymium is not that expensive, and most come from China. That's the other problem. So people try to get rid of these dysprosium magnets and still retain a pretty stable Curie temperature. Okay, but that's another thing. So this can be determined just taking the minimum of this function here to find the the inflection point here, and you find out that this psi star at which the transition occurs is minus alpha 0, or the solution for the minima here. You can use all what you learned in high school, I think, to determine the minimum of this function here, and then you find this behavior. Now if we go, or if we want to describe second order phase transformations, we have to go a bit further. Further in this Taylor expansion. in principle, there's no need to put these factors on force. It's just so you add a term of 6th order. As before, alpha 0 has to be positive, but now beta is negative and gamma is positive. And what you obtain then can be seen here. This is for high temperature. At high temperature, so at 20% above the critical temperature, these temperatures are multiples of the critical temperature. You find a single minimum here at 0. But now if you approach the critical temperature, a second minimum shows up here. But there must be something wrong, sorry for that. Maybe I should, I did this very fast this morning, so I better do it by hand. I will explain what is wrong in this curve. So at very high temperature, you find a single minimum here. If you lower the temperature, you develop extra minima here. Maybe I should put a much larger and here a bit larger. And this already shows some interesting property of first order phase transitions. Yeah? Here you have a local minimum. I come back to it. Now if you go even deeper, this would be at the critical temperature. What do we see here? We have one minimum here. Sorry, this should be at 0. Maybe I should just shift my axis. Okay. So you have a minimum of the free energy of free enthalpy at 0 order. But you have another minimum here at a finite degree of order. And only if you go below sorry. This minimum is deeper than this one. And at very low temperature, this minimum converts into a maximum. So this. And I don't know what went wrong here when I made these plots here. Probably I made a mistake with the parameters here at the critical temperature, the orange one. This minimum here is already far deeper than this position here, so I don't know. So what does it mean? First of all, it means that the equilibrium degree of order, which is 0 here, at the critical temperature jumps to a finite value. This is what we expect for a first order phase transition, an abrupt change in order. sorry, I always use S here because in my manuscript some time ago I used S here, but that's so the degree of order slightly goes down if you go up here. So this minimum here moves a bit to the left, but then at the critical temperature it jumps here. How does this relate to what I said before, that first order phase transitions are related to a jump in entropy? I think it's more or less intuitively clear that entropy and degree of order are directly related. Yeah? So if the degree of order jumps, we expect also to have a jump in entropy. So this would correspond also to the entropy. That's the first point. But the second point, which is perhaps not that obvious from what I explained before, is, but it's known to everyone, I guess. So if you start in this low temperature phase, or we can also start in the high temperature phase. Here in the high temperature phase at degree of order 0. Now you develop this side minimum here. You have a minimum here, but still if you start in this disordered state, you would have to overcome this barrier here. This, I don't want to call it an activation energy, but there is a higher energy which has to be overcome to move from this degree of order to this degree of order. So we have something we call metastability. Yeah? So the system would stay for some time in this disordered state, even if you're somewhat below the transition temperature, still there is a metastable minimum here. Yeah? And only if you're here, this is the loss of stability here, then the system would spontaneously do the phase transition. Yeah? And that's something we always have to struggle with. Yeah? If you are studying all kinds of phase transformations on a computer, that you have this metastability. I think Guru mentioned it for the melting transition. The melting transition can be also described by such a formalism. So that's some characteristics for first order phase transitions. An activation barrier and normally this is done by some nucleation events. So this extremely simple model of Landau already captures big part of the interesting characteristics of these phase transitions. And I think I skipped some part of what I prepared here. Perhaps just very briefly, what I did here until here was just G of t. But of course, you can also consider further thermodynamic parameters like the pressure. And I guess you know that pressure will shift phase transformation temperatures. So if you have a gas-liquid transformation, for example, this curve of free energy becomes a surface of free energy. So in the PT plane here, in the gas phase and the liquid phase, they have different, and they have not an intersection point, but an intersection line. And this you can project down to the PT plane. To the left you have liquid, to the right you have the gas phase. This is what is typically shown as phase diagram of liquids in the PT plane, yeah, of many materials. Here you see the example of water. So you have the vapor phase, there's the liquid phase, you have water is very complicated, different ice phase, different crystal structures. And here the pressure axis, that's particular for water or ice, that this melting curve is bent to the left, not to the right, like for most other solids. But here you also see this critical point. Yeah? Here the difference between liquid and vapor disappears at this pressure and temperature. And you can take these phase diagrams in the pressure-temperature plane for many other phases. These high pressure phases are interesting for geology, for example. No, I think we can skip this. I think this is the last thing I wanted to show. This order, no, there are more things, but briefly. This order-disorder transition, because this is a nice example which one can easily treat without these ad hoc assumptions in the Landau theory. What comes out is very similar, yeah? But it's a bit more a microscopic picture as this Landau theory. So that's this case I already described. The body-centered cubic lattice, for example, in beta brass, copper zinc. So below the transformation temperature, you get this type of order, which is called B2 structure, at least in one of the many terms to denote different structures. How can we describe it? How can we define an order parameter? We can take the number of A atoms or B atoms sitting on the corner sides and sitting on the body-centered sides. I call it A alpha, A beta, and similarly B alpha, B beta. And if we are 50%, A alpha plus A beta is half of the total number of atoms, same for B. And then we can define an order parameter as a difference in occupation of the alpha sublattice, these sides and these sides, divided by the sum of those. And then in a simple approximation, which I don't write down, but it's very simple, you can calculate the internal energy of such an arrangement. Basically, what you do is to count the number of AA pairs, BB pairs, AB pairs. And then, since you have very simple sum rules, finally you end up with this expression here. There's one further assumption, the so-called mean field approximation, or two further assumptions. First, I assumed that there are only next neighbor interactions, so only from the corner side to the body center side. not across lattice constant here. That's the nearest neighbor interaction, but that's very simple to generalize. And this mean field approximation, what does this mean? It means to count the number of AB pairs, for example. I can start with an A atom here, and then I have to know the probability that there is a B atom on the neighboring side. And the approximation which is done here is that this probability is just the occupation of these sites with B atoms. So this B beta. Yeah? If you make this assumption, you end up with this simple expression for the internal energy. That is, as we had before, the number of next neighbors, 8 in this lattice, N is the total number of atoms. Epsilon is what we call the pair exchange energy, the difference in energy between AB pair and an AA plus BB pair. Yeah? So if this is positive, this means that the energy of an AB pair is higher than this AA-BB pairs. This would mean that we go in a precipitating system. If it is negative, that means that AB pairs are favored, and then we have what we want. Next is the entropy, what we need. And I think I showed it already in the last lecture or so. You just do it by this simple number counting. You get all these logarithmic terms, except that we do it separately here for the two sublattices. Here you have the alpha sublattice and the beta sublattice. And if you go through it, perhaps it reminds you of something I already showed. You have this x times ln x terms here. In this case, it's 1 plus s, the order parameter. Here I call this order parameter now s, not psi, but it's the same what I called psi before. So the number of possibilities you obtain like this here, these two terms here, and multiply it with minus kb and the number of atoms here. So the total free energy of this system in this simple approximation is this here. And now you obtain, if you plot this as a function of s without this Landau approximation, you get a set of graphs which extremely resemble what I showed before, now based on a kind of microscopic model. Yeah? So this is very nice, I think. And you see here at the temperature above the critical temperature, there is one single minimum here. And if you approach the critical temperature, the curve here becomes flatter. That's at the critical temperature. Below the critical temperature, this converts it to a maximum. And you get these minima here and here at plus minus. Plus minus just means that I can put the copper atoms on the copper side and the zinc atoms on the body centered, or I can put the zinc atoms on the corner sides and vice versa. So it's just an inversion of sign, and this is visible here in this definition of the order parameter, which can be plus or minus. In this way, you can calculate the equilibrium degree of order, which shows a very nice second order phase transformation. So that's a second order phase transformation. Then hopefully there's also a first order phase transformation. And for this, you have to go to another type of lattice. You go to the FCC lattice. And the FCC lattice can be considered as consisting of 4 sublattices, 1, 2, 3, 4. So the corner side and the 3 face-centered sides. And you can, very much as before, you can use the occupation of these 4 sublattices with one species, the B atoms here, for example, at 25%. If all sublattices, in this case copper 3 gold, you have 3 copper atoms, so you put the copper atoms here on the face-centered sides and the gold atoms on the corner sides. Then you obtain a structure called L12. Don't ask me, this nomenclature is completely unsystematic and in some respect even wrong. This is a space which was thought as what the superconductors have. No, not the largest. Don't worry. No. It has a name like this one. These intermetallic phases.
1, 2, 3.
Yeah, these are the high temperature superconductors, but that's again another type of denoting the phases. No, I was A15 phase. So A in this type of naming is meant for pure elements. A1 I think is BCC, A2 is FCC or so, and A15 is supposed to be a pure phase. And this was because erroneously they thought tungsten shows a phase transformation. Later on, much later, after they gave this name to a particular phase, it turned out that it was a tungsten oxide. Yeah? But these A15 phases, they are the low temperature superconductors, yeah? Like, what is it, tin, germanium 3 tin or so, is one example. Yeah. Okay, so this is this L12 phase here. There's also an L21 phase, which is completely different, so don't try to understand these names, but they are common. So, and we can define an order parameter like this here. You take the occupation of one of the sublattices minus 1/3 of the sum of the other 3 sublattices. I should have called this one 1 here. So if all sublattices are equally occupied with 1/4 of the p atoms, you get 0 here. If all are sitting on one sublattice, here say on sublattice 1, then you get an order parameter 1. So that's a reasonable definition. And by going through a very similar calculation, you obtain a free energy now of this form here. Sorry, again, I changed the terms here. So xi is the occupation of the sublattices. That's as before. There's a sum over I missing. Omega is what I called epsilon before. But anyhow, and these are the terms for the entropy here. Sorry, I forgot the sum over I here. And if you choose this phase here, you can plot this as a function of the order parameter. At high temperature, you have this single minimum at order 0. So all the B atoms are equally distributed among the lattice sites here. If you lower the temperature, this is here very high temperature, 5% above the critical temperature. Here at 1% above the critical temperature, you see that such a side minimum is developing here. Precisely at the critical temperature, you have this minimum here, and still the other minimum here. And if you go lower, 2% below, you find this minimum here. It's still a minimum here. So the metastable disordered state. Here both have equal stability. Here you have a metastable ordered state. And only at temperature here at 5% below, you find this minimum here. This now is asymmetric, in contrast what we saw before, because this order parameter is asymmetric. So it would matter if you exchange these sublattices here. If you put this sublattice 1 here in this sum, yeah, that's why it is asymmetric. But nevertheless, you can translate this into an order parameter. So at high temperature, the minimum is here, the order parameter is 0. And at very low temperature, the order parameter is 1. You have this slow decrease in order, so you can always put this equilibrium degree of order here to this curve here. And here you find this abrupt jump from finite order, 1/2 or so, to 0. That's why I like these disorder transitions. You find both types of phase transitions here, depending on what type of lattice and what other assumptions you make. And this is can be verified in Monte Carlo simulations. In Monte Carlo, you don't have to make this mean field approximation, but still you find a second order phase transformation for the B2 to BCC transformation, and you find a first order phase transformation and the transition from FCC to L12. And similarly, you find it also if you do a two-dimensional simulation. I think we showed these examples. Perhaps I show them in the next lecture on Introduction into Monte Carlo. In a two-dimensional system, if you use a square lattice in a 50% ordering, you find a second order phase transformation. If you use a triangular lattice with a 1/3 occupation, so you have 3 sublattices, you find a first order phase transformation. And you nearly see this, you nicely see this metastability there. I show it in the next lecture. Okay, so this was an example of the order-disorder transformations. I skip this here. I keep it for the next lecture. 2 further examples, very simple ones. Martensitic transformations, so examples for this displacive transformations. Who never heard about Martensite transformation? I don't know whether it's treated in, say, chemistry or physics lectures. It's on the basis of steel hardening. Steel hardening, I guess you know. You heat up the steel to high temperature, and then you rapidly quench it. If you would slowly quench it, it would do a precipitation reaction. An iron carbide precipitates. If the time is not sufficient to form the precipitates, then nature must find another way to get rid of the free energy, and that's this Martensite transformation. So I want to briefly explain it because it's an example of such a displacive transformation. So that's the BCC lattice here. Oh, it's the wrong way around. So I rapidly copied these slides this morning from another lecture. It's a bit stupid now. So it's a transformation from BCC. I mean, you know that iron has these allotropes. At low temperatures BCC, at higher temperatures FCC, and even higher temperatures again BCC. And how can you go from a BCC to an FCC phase? At least this I can explain here. If you go to the FCC, oh no, it's, sorry, I confused. That's a high temperature phase, the FCC phase. Yeah, it's a gamma iron here. So gamma iron is FCC. And you can use another unit cell in the FCC lattice, like this one. This is not a cubic, but a tetragonal structure here. Yeah? So this is half of the diagonal here, and that's the cube axis here. So it's a tetragonal unit cell. But if you choose this unit cell, you already see it's a body-centered tetragonal phase. And now if you want to transform from this FCC or body-centered tetragonal phase into a body-centered cubic phase, this one, you just have to slightly displace the atoms. And this is what is known from these displacive transformations. You slightly shift the atoms, and you do it the same in all the unit cells. Yeah? So they do it all in parallel. This is how you can transform from FCC to BCC by just I mean, it's exaggerated here, a few percent of the lattice constant or so, these displacements. Now, just to complete this, what happens in martensite? You know that martensite is a very hard and brittle phase. In principle, the same happens. Where are the carbon atoms located here? They sit on certain interstitial sites, the tetrahedral sites, no, the octahedral sites, and these octahedral sites, they can be put here on the axis, on the side axis of this tetragon. Yeah? And now if you do this transformation, the carbon sitting here, I mean, not each site is occupied, only a small fraction of the sites is occupied. This prevents the transformation into this complete cubic phase. So it stays a bit tetragonal. And since this tetragonal phase can have different orientations, like this, or like this, or like this, you have different variants, and this huge number of variant boundaries, they prevent dislocations from motion. So that's basically the martensitic transformation. There's one important point. This martensitic transformation is nearly volume conserving. If you have a volume conserving transformation, you can write down the transformation matrix and you find that there are invariant planes. Yeah? And these invariant planes, that's where this shear takes place, and hybrid planes and so on. Yeah. I skip this. Okay, and the last example I wanted to give is the omega transition. Okay, it's in zirconium. Zirconium undergoes also a transformation from BCC to hexagonal. And this transformation can be visualized if you look at the cubic unit cell, at the body-centered cubic cell. You already see that this resembles these 1-1-1 planes of the FCC lattice or the 0001 planes of the HCP lattice. So this looks like a hexagonal cell here. And now, if you plot these 1-1-1 planes into the cubic lattice, you slightly displace them against each other. One plane slightly shifted up, the other one slightly shifted down. So if you shift this down and this up, then you obtain the hexagonal plane. Yeah? So you have the stacking A, B. If you merge these two planes, A, that's the stacking of the hexagonal phase. And what does it mean? This means this plane moves down, this plane moves up. And think back of what I said about lattice vibrations. This can be considered as a frozen-in lattice vibration. Yeah? So the lattice starts to vibrate, and the energy required for the vibration gets smaller and smaller. At some point, the atoms freeze in here. So this is sometimes called, I think I mentioned this, not a frozen phonon, soft phonon transition. And it's visible here. I showed this type of graphs already last week here. These are L stands for longitudinal phonons. So these are the vibrations in the, or with a vibration direction perpendicular to the plane here. These are transverse phonons, which does not matter here. And you see that there's a minimum here. So this means that such a oscillation here, this at elevated temperature, requires only low energy, and if you go lower in temperature, this goes to zero, and then you have this transition here. So you can plot this displacement here, such a sine curve. That's a typical soft phonon transition, and I think it can be seen also in the electron microscope as small regions which transform then. Okay, I also prepared something on solidification, but I think you will speak about this later on, or you did already last lecture.
Yeah, we looked at the melting point.
Yeah.
And we will also look at the interfacial energy anisotropy.
Yeah. I mean, I can show these slides since I have them. That's the solidification of Lennard-Jones argon. Here is a function of temperature, the total energy, and if you look closer, if you take the derivative of this curve, this is just from an MD simulation here. If you look closer, you find this maximum here, where the solidification starts, or the melting, go in the other direction, starts. And perhaps just to show how to evaluate, I think you will also say something about the visualization, how you can study, if you have such a molecular dynamic simulation, you want to learn something. Also, if you would do such a simulation for such a system, there are useful tools in this Ovito package which allow you to characterize structures, and one is the so-called centrosymmetry parameter. The idea is that you look around one atom, do the neighboring atoms, are they symmetric around it, or does it deviate from symmetry? This allows to characterize different structures. So in a hexagonal structure, you would find a nice value close to 0. And for other structures, you find other values. And here, if you do it for a liquid, the centrosymmetry would be pretty large. And then if you go to lower temperature, then suddenly this becomes close to 0. I think I have to, I can't accelerate it because it's just taking a movie, so we have to wait here. These 200 frames. That's one thing you can also do with this Ovito software. You can take a couple of configurations, and then you can make a movie out of this. Now you see that the crystallization sets in here, for example, and here you see that the maximum in this centrosymmetry parameter close to 0 builds up here. So this FCC structure is centrosymmetric, while the molten structure is random. And now here at very low temperature, you see nicely the crystal structure here, and this other part completely vanishes. Or the pair distribution function, so what is the probability to find a certain number of atoms around a given atom in a shell. That's what we call the pair distribution function. Again, you can follow the pair distribution function here and during this solidification process using this Ovito tool. Third one is a common neighbor analysis, which allows, I think that's what you used when you showed this stacking faults. It allows to distinguish between different types of crystal structures, FCC, HCP, BCC, and icosahedric, for example. So you take the local environment whether it resembles an FCC structure, that's this, what is it called, dodecahedra, and the other structures here. And again, you can study this, And this, I think this is what you already showed if you go through the temperature and you can pinpoint this transition temperature. But what you typically do, what Guru already showed, is that you start with a half molten, half solid system, because you have this metastability in the first order phase transition. So you must somehow overcome this metastability, and that's by giving a nucleus of both phases, and then you decide, does it go into this direction, then you're below the melting point, or does it move in this direction, then you are above the melting point. Okay, so this was about phase transitions, which is a very general phenomenon nearly everywhere in material science, I would say. Without phase transitions, you hardly have any usable material. Okay, so thank you for the moment. This is to briefly introduce the basic ideas of Monte Carlo simulations. Once in a while we already heard about it in other lectures, but maybe it's worth to explain it more in general. First, where comes the name from? Monte Carlo, I guess you all know, is I think it's a city on the Mediterranean Sea with a big and famous casino, and here the people are gambling. Some apparently are gaining a lot of money. And the name was given to this method because it involves some random processes. Yeah? I already said that in molecular dynamics we're quite limited, but most algorithms in molecular dynamics, they are deterministic. You have your trajectories of atoms, you integrate it, and then you arrive at a point, and you can even invert the direction of time, then you go back to the initial point. This is a bit not valid for all types of, if you use barostats or thermostats, where there's this Langevin thermostat which adds these random forces, then it's not time reversible. But there's not much of randomness involved here. In Monte Carlo simulations, it's different. In order to tackle more complicated processes, you jump across many molecular dynamic steps, so to say, or steps in nature, and just do one huge step. But the choice of this huge step must obey some statistical relations. And this is done by this randomness. The people who invented this method, or at least some of them, shown here, Nicholas Metropolis, who is responsible for this Metropolis algorithm. I think these letters here, this because these pictures come from Los Alamos National Lab, where these people were employed, and these pictures were taken for their ID cards there. So these two, I think Stan Ulam and Nicholas Metropolis, were the major ones. John von Neumann, I think he was German by origin, but presumably he was a Jew and had to immigrate during the Nazi.
Hungarian.
He was Hungarian?
Yeah, I think he's also Hungarian.
I see. Stan Ulam, I don't know. He was.
Ulam also probably, because there was this cafe
Mhm.
where they will all study mathematics, they will get together to solve problems.
I see, yeah, I
This
remember.
mathematician Brewer or something.
Yeah. And there's another name we will come across, Andrei Markov. I think he's Russian, yeah, but he was, as you see from the picture, sometime before. But he laid important fundaments for this methods, or which are applied in the method. I made a note here that an uncle of Ulam, he was a gambler and lost a lot of money in Monte Carlo. That's apparently why he chose this name for the method. Yeah, so probably he also thought about random processes. So the basic idea is to describe the evolution of our system, now not by these very small steps we do in MD, but by much larger steps which are more or less independent of each other, but the transition between different steps has to obey certain rules chosen from statistical physics. This chain of independent states is called a Markov chain. That's where this name comes in here. So perhaps I should again make a few notes. Like in so we have a starting configuration C1. We make a transition to another configuration, and so on. And we assume that there's no memory in the system. So once you are in configuration 2, you lose the information about configuration 1. That's what we call a Markov chain. As Gu also already explained, there are much more applications of Monte Carlo methods as the ones we study here for diffusional phase transformations. For example, in mathematics, to do complicated integrals or just do simple integrals to obtain pi. I think that's not a real application. I mean, there are other ways to calculate pi, but I think there is I forgot the details, but you can calculate pi using a set of needles. You throw the needles on a floor like this, and you count the number which intersect the lines between these floor plates here, and the probability that a needle is oriented in a proper direction.
Buffon's needle problem or something it is called.
Okay, I don't know the name.
Which is similar to the way, for example, we evaluate intersect method to get the area and so on.
Yeah. And of course, this is much faster as MD, can cover much larger time scales as MD, because this step from one configuration to another configuration can be like a diffusional step. Yeah. So. And the first thing I want to discuss here is what we call equilibrium Monte Carlo or so. How can we do this procedure? I mean, of course, we can always do some changes in microstructure, or we can put atoms from here to here, but this does not help to understand material properties. So we have to introduce certain rules for these transitions from one configuration to the other in order to get some information out. Before this, I will show, or I think I said it already, how to deduce information out of such a Monte Carlo simulation. If you have such a chain of configuration, which obeys our rules, then we can easily calculate equilibrium properties, expectation values of certain quantities, for example. This is just the value of this quantity in each of these configurations. Times, and this is the critical thing. About Monte Carlo, times this Boltzmann factor divided by the partition function. Now one might ask, how can I choose the configurations or transition between configurations? Of course, I could start, let's think of a very simple example. I think I have one here on one of my slides. One could start with one configuration where you put red atoms randomly onto a blue lattice. Then I could start to evaluate one configuration after the other. So I put this atom from here to here. Can't see what I'm showing. From here to here, from here to here, from here to here. Same with this atom here, and so on. So you can try to sample the whole configuration space systematically. But that's a very limited possibility. Maybe if you have 3 lattice sites or so, this might be possible, or 10 or so. So we want to sample configuration space. If I have, for example, 1,000 atoms, and with 10% of B atoms. Any estimate how many configurations we would have to sample? What would you think? Probably it's a large number, yeah. I mean, it's all this binomial terms, yeah. This binomial 1,000 over 100, which is roughly 10 to 140 configuration. So if you want to sample such a small configuration space with only 1,000 atoms, systematically, I think the age of the universe would not be sufficient. So if you make, I don't know, 10 to the 9 samples per second, yeah, this would require, what is it, 10 to 32 seconds. A year has 3 times 10 to 7 seconds. So you see it's, let's say a year has 10 to 8 seconds, then we are at 10 to the 124 seconds, years, 10 to 124 years. The age of the universe is roughly 10 to the 10 or so years. So no chance, yeah. So you need 10 to the, I'm lost, 100, 10 to the 100 something times the age of the universe to just sample this very small system. So no chance. That's all I wanted to say, yeah. And if you have larger systems, it's getting even worse. Cannot be worse than this, but okay. So we have to find a way to efficiently sample the configuration space. What does it mean to sample the configuration space efficiently? If you look at this expression here, since it has this exponential here, some configurations contribute a huge amount to this sum, others hardly anything. So you must try to find only the relevant configuration, the important one. That's why this method is called importance sampling. So on this chain, this Markov chain, you try to go along the important. I prepared this talk. I thought about certain expressions we use in German. And I don't know why, but if you irrigate your flowers or so, you use a watering can. You just, in German, if you distribute something very at random, this is called, you spread it with a watering can, which is not what a watering can is meant to. I mean, you do it very targeted. Yeah, so you don't want to use this watering can all over, but you want to spot at the relevant points. Yeah. So I don't know why in German this strange use of this term is common. For example, if money is distributed among everybody, it's called the watering can, the Gießkanne. In German, it's stupid. Okay, so how can we achieve this? You see that here the terms with very large energy result in very small contributions. So somehow you must stay at the states with low energy. But not only at the lowest energy, then you are stuck in something where you lose the entropy. Yeah? So somehow you must find the good compromise between the low energy states and the slightly elevated energy states. So you sample sounds complicated, but it turns out to be very simple. Most to these expectation values or to the partition function. This can be obtained if we do the changes, the jumps from one configuration to another according to their thermal probability. So if you are in a low energy state and you have a somehow neighboring state, yeah, with slightly higher energy, then you can go there using this Boltzmann probability, but it makes no sense to go to a state with an extremely high energy. Then, yeah, I mean, this state is, so to say, lost. Yeah. So this chain, this Markov chain, is obtained with the proper thermal probability of the states. If a transition from configuration I to I plus 1 or 1 to 2 so we have this probability for the transition 1 to 2 times the probability to be in state 1. So perhaps I should define the terms here. Probability to find our system in configuration 1. And think, if I speak about the configurations, just think of an arrangement of the red atoms on the blue lattice, yeah? And pi C1 to C2, the probability per time to go from C1 to C2. So this product must be equal to the backward transition Why is it important? Each of the configurations has a certain thermal probability. So the system can undergo a transition from here to here, or could undergo a transition from here to here. Think of two configurations, one with a slightly higher, one with a slightly lower energy. So I have my system in configuration 1, and I want to know, does it go to configuration 2? So I have this probability to go from here to here. And to go backwards, of course, this would have a higher probability, but the probability to find the system in this state is lower because it's a higher energy state. So if I adjust the transition probabilities so that they reflect the probabilities in each state, then I sample the system with all the right probabilities. So I should try to put this here. So our probability, like this. These probabilities, yeah?
This expression that you have written of P.
Oh, sorry, yes. Is it what you meant, yeah?
No, sir, I'm saying that this is the equation for what we call as the detailed balance.
Yes. It means if I have few systems or low probability to find the system here and high probability here, then there must be a large probability to jump from here to here and vice versa. This is, you're right, it's called the condition of detailed balance. So perhaps before I continue here, these probabilities we already encountered. That's the exponential minus the energy of configuration 1 divided by kBt, divided by the configuration or the partition function. I call it z here. So if you put this in here, you see that z cancels out. So it's just the exponential of minus EC2 divided by exponential energy of configuration 1 over kT, or and this now must be equal to these probabilities here. So there's a probability to go from C1 to C2. Divided by the probability for the reverse transition. So our transition probabilities to go from one configuration to another configuration must obey this rule here. Then we will find our configurations according to their thermal probability. I can write the word here. That means if I construct this chain of configurations here, where is it? Here. And I choose my transition probabilities from one to the next configuration according to this law of detailed balance, then I obtain these configurations the probabilities of the configurations with the thermal probabilities. So this is more or less nearly all we have to know about Monte Carlo. The rest is, there's a lot of freedom. At least if you are studying equilibrium properties. So if we obey this law here, then maybe some methods are more effective as other ones, but we don't make a mistake. The situation is different if we want to choose or if we want to consider this chain of Markov chains as a kinetic evolution of our system. If we study the evolution, say, of a precipitation reaction, then the details of this transition are much more important. I will speak about this also I think in the next talk. To study equilibrium properties, this condition is sufficient. So what can we do?
If we do kinetic also, we will call them as Markov because now it will have some sort of memory, right?
I think not, because the transition does not depend on the step before, the transition probability. This is still a Markov chain, but yeah, of course the evolution of the system itself, it follows some evolution. So so maybe detailed balance is sufficient. That's one case if we study evolution to equilibrium, but there are other cases as well. These are non-thermal systems. Long time ago, I studied quite a lot irradiation effects, where besides the thermal transitions, the diffusional jumps, you have forced jumps, so you have a fast ion incoming or an electron incoming, which kicks out the atoms from their rest places. Yeah? If you have such a type of kinetics, which does not follow the laws of thermodynamics, again, this becomes very important, which details you choose for your Monte Carlo step. Details of the transition probabilities. Become important. An example could be, in this simple case here, that we choose as a step from one configuration to the other, that we interchange neighboring atoms or arbitrary atoms. Yeah? Anything would be fine for equilibrium. For the evolution towards equilibrium, it's clear that it makes a huge difference whether I just exchange nearest neighbors or whether I exchange distant neighbors or whether I use vacancies. Yeah? Yeah, something like this one could do to study equilibrium properties, but for non-equilibrium, this is not a priori clear. So what type of choices can we have, and how can we technically proceed? I think this was also already mentioned in one of the former presentations. If we have our we want to go from configuration 1 to configuration 2, one choice could be that I do the exchange or the jump if the energy of the final configuration is lower than the starting configuration. So this means I always walk down the hill and I walk up the hill if I have to spend energy. If both are equal, you see that both conditions are fine. So if you have a kind of energy landscape, configuration 1 and 2, first situation, so this is the energy, first configuration, supposed to have a higher energy. Then we do this jump for sure, probability 1. If we now interchange C1 and C2, if we want to go up the hill, we do it with this probability. Now we can check whether this condition of detailed balance for this choice is fulfilled. In principle, we would have to check two situations. Let's just look at the if the energy of the starting configuration is higher than that of the final configuration, then this is 1. And this is just this exponential term here. But now we have to interchange here, because now we start from C2. And this is the condition we have to fulfill. Somewhere it is here, yeah. And if you do the other way around, the starting configuration is lower energy, then you just revert these terms and it's also fulfilled. So the detailed balance is fulfilled. This one is a choice one can take. Another choice again, I'm over time. I thought this one is short here. Shall we make a break and continue after lunch? Maybe I'll just finish these simple cases here, because I mean the other ones are very similar, and then we make a break for lunch. Sorry, it's not p, it's pi. You can just put here exponential minus divided by 2 kBt. I explain in a moment, if I show the next one, what it really means. I choose this probability with a factor 1/2 here. So the backward transformation would be the same. Except that I change the sign here. And again, if you take the ratio, you readily see that the condition of detailed balance is fulfilled. Yeah, I think it's very simple. Just put an OK here. Or is there any, I mean, if you take the ratio, you see that you get what you want. Perhaps more interesting, because this becomes relevant for kinetic Monte Carlo, is this case C. Let's look back here to the situation. If I have my system in state 1, I have to overcome somehow an energy barrier, a saddle point. So the probability in a real physical system to undergo a transition from here to here is that by a fluctuation it obtains the energy to go up to the saddle point, and then it spontaneously goes down. So a more physical choice then is for this transition probabilities C1 to C2. That we have the energy of the saddle point minus the energy of the starting configuration, independent of what we choose for the energy of C2. Yeah? I mean, that's the physical idea behind it. We go up to the saddle point and then we move down. So reverse transformation or transition would be C2 to C1, which then is the same but with C2. Now if you form this ratio, you see that this factor exponential minus ES over KT, same here and here, cancels out. So what we keep is exponential plus EC1 over KT times exponential minus EC2 KBT, which then again is what we want to have, this condition of detailed balance. So more or less, this would be the form of this transition probability which we should choose, but we will see this can pose a technical problem. And just to come back to this one here, this just means that I put the saddle point energy in the middle. So we have here energy of C1, here we have energy of C2, and in this example B, or in this case B, we put the saddle point as an arithmetic middle of EC1, EC2. This you can easily check. So B Okay. I think I stop here, and then we continue after lunch with some more details. How do you technically implement this construction of a configuration chain? Okay, so thank you and good appetite.